formal theorem proving in Lean 4, has seen massive gains from scaling proof generation and verifier-aware training. But there's a persistent bottleneck. Agentic proving is almost always treated as an inference time wrapper, not a learned policy. This creates a train-inference mismatch. The model learns from static, final proofs, but at deployment, it's expected to handle multi-round retrieval, compiler feedback, and iterative repair in distributions it was never optimized for. Today, we're looking at OProver, a unified framework for agentic formal theorem proving released by the MAP team. OProver closes this gap by treating proving as a retrieval-grounded, feedback-conditioned refinement loop, and it trains the model end-to-end to use these signals as part of its core policy. We'll dive into the OProof's corpus, the co-evolution pipeline, the specific GSBO reinforcement learning setup, and why a 32 billion parameter dense model is now achieving state-of-the-art results against 671 billion and 560 billion parameter competitors. Let's start with the core methodology. OProver formulates theorem proving as a bounded multi-round refinement process. At each round, the policy conditions on a compact interaction state. This state is defined as the target theorem statement, the retrieved proof context, the previous proof attempt, and the compiler feedback from that attempt. Crucially, the policy does not condition on the full interaction history. It only sees the most recent attempt and its feedback. This keeps the state compact, preserves the local correction signal most relevant for proof repair, and ensures the training time interface exactly matches the proving time interaction. This is a key modeling choice. If the model were trained on full histories but deployed with a compact state, or vice versa, you'd see performance degradation due to distribution shift. OProver eliminates this by design. At each round, the prover queries a retrieval memory for the top K compiler-verified proofs using semantic similarity. The retriever used here is QN3-8B embedding, chosen over Gödel's internal retriever because it provides a broader similarity score distribution, leading to more discriminative ranking and better top K selection. When a proof attempt fails verification, the Lean 4 compiler returns textual diagnostics. OProver passes these diagnostics directly to the policy as raw text, without projecting them into a hand-designed error taxonomy. Preserving the raw textual form allows the policy to condition on fine-grained information, like specific type mismatches, unknown identifiers, or unsolved goals, that would be lost under categorical encoding. This raw feedback is essential for targeted revisions that distinguish multi-round refinement from repeated single-shot regeneration. Now let's talk about the data. You can't train a policy to use retrieval and repair without data that contains retrieval and repair. Existing formal corpora mostly preserve final verified proofs. OProver introduces OProofs, a large-scale corpus designed specifically for agentic proving. OProofs contains 1.77 million unique Lean statements and 6.86 million compiler-verified proofs. But the value isn't just in the proofs, it's in the trajectories. OProofs include serialized proving records that capture retrieved context, failed attempts, compiler feedback, and subsequent repairs. The corpus is built from three sources: public Lean resources, large-scale proof synthesis with compiler verification, and traces from OProver's own agentic proving. This leads to the framework's second major contribution, a co-evolution pipeline. Training proceeds in an iterative loop. The current prover generates new verified proofs and repair trajectories. These are recirculated back into OProofs and indexed into the retrieval memory. The data, the training procedure, and the proving policy co-evolve. Each iteration makes the corpus richer and the prover stronger. Algorithmically, this looks like this. You start with a continued per-training base. Then for each iteration, you run agentic rollouts. You extract round-level repair examples for supervised fine-tuning. You identify hard cases where the success rate is non-trivial, meaning some rollouts solved it, some didn't, for reinforcement learning. You index the new proofs into memory. You update the model and you repeat. Let's get into the training details. OProver base is obtained via continued per-training on a 65 billion token mixture. This includes Lean data, code, mathematical reasoning, and long chain of thought data. From the base, iterative post-training alternates agentic proving with SFT and RL. For supervised fine-tuning, the rollouts are decomposed into round-level repair examples. The model is trained to predict the revised proof attempt given the state. The loss is computed only on the target proof attempt, providing process-level supervision across multi-round rollouts. For reinforcement learning, OProver uses Group Sequence Policy Optimization, or GSPO. This is a sophisticated RL setup. For each theorem, the model samples multiple multi-round agentic rollouts. All rounds across all rollouts for the same theorem are pooled into a single group. The reward structure is specific. If a proof attempt is verified by Lean, the per-round reward is 0.8 plus 0.2 times an indicator for format correctness. If it fails, the reward is 0. Format correctness is rewarded only when the round is actually verified. Advantages are computed by group relative normalization across this pooled set. This allows the policy to learn from contrasts, both across independent attempts and across successive refinement rounds within a single rollout. This pooled normalization is critical for stabilizing learning in this agentic setting. Now let's look at the results. OProver 32B is evaluated across 5 benchmarks, Mini-F2F, MathOlympiad Bench, ProofNet, ProverBench, and Putnam Bench. OProver 32B attains the best pass at 32 on Mini-F2F at 93.3%, ProverBench at 58.2%, and Putnam Bench at 11.3%. It ranks second on MathOlympiad and ProofNet. This gives OProver 32B more top placements than any prior open-weight whole-proof prover. The scale comparison is striking. OProver 32B is a 32 billion parameter dense model. It outperforms DeepSeek Prover V2, which is a 671 billion parameter model across all 5 benchmarks. It also outperforms Longcat Flash Prover, a 560 billion parameter mixture of experts model, on Mini-F2F, ProverBench, and Putnam Bench. The only exception is Longcat on MathOlympiad Bench. These gains are driven by the training methodology, not model scale. We also see strong scaling behavior at test time. OProver benefits significantly from additional test time compute. As the total budget increases, success rates improve. However, there are diminishing returns. The rate of improvement shrinks as the budget grows. More interestingly, the optimal allocation of compute between refinement depth and sampling width depends on the benchmark difficulty. On easier benchmarks like Mini-F2F, performance improves monotonically with refinement depth, peaking at a depth of 16. On the hardest benchmark, Putnam Bench, the optimum settles at a depth of 8. This makes sense mathematically. On hard problems where per-chain success probability is low, you need width to find a viable path. Pushing depth too narrow kills exploration. On easier problems, where success probability is higher, deeper refinement pays off because the model can reliably repair partial successes. This benchmark-dependent trade-off is a key insight for deploying these systems. Ablation studies confirm the drivers of performance. Removing multi-turn compiler feedback causes the largest degradation across all benchmarks. For OProver 32B, pass at 32 drops from 93.3 to 88.4 on Mini-F2F, and from 11.3 to 7 on Putnam Bench. This confirms that iterative refinement is the primary driver of gains. Removing retrieval also hurts, but the impact is smaller. Retrieval provides complementary benefits by grounding the proof with relevant lemmas and tactic structures before refinement begins. The synergy between retrieval-augmented grounding and compiler-guided refinement is what makes OProver effective. Finally, the iterative coevolution loop yields measurable improvements at every step. Evaluating checkpoints across post-training iterations shows monotonic gains. OProver 32B rises from 84.7% on Mini-F2F after continued per-training to 93.3% after 2 post-training rounds. Recirculating verified proofs and repair trajectories continuously strengthens the prover without saturating. To summarize, OProver presents a unified framework that treats agentic formal theorem proving as a learned policy rather than an inference time heuristic. By constructing the OProofs corpus with trajectory-level supervision, training with round-level SFT and GSBO, and implementing a coevolution pipeline, OProver achieves state-of-the-art results among open-weight provers. The results show that a 32 billion parameter model, trained with this agentic policy, can outperform models 10 times its size. The framework sets a new standard for data-centric AI in formal math, demonstrating that the path forward lies in aligning training data and policy with the multi-round interaction dynamics of the verifier. For the code, the OProofs corpus, and the full paper, check the link in the description. Thanks for watching.